We're now taking a look at some standard examples of curves and surfaces. Namely, we're going to look at conic sections, which are ellipses, hyperbolas, and parabolas. And we're going to look at their higher dimensional analogs, which are quadric surfaces, ellipsoids, paraboloids, and hyperboloids. These are standard examples that we have run into before and will continue to run into, especially in integration. And well, in terms of their relevance outside of calculus class, obviously, conic sections are very relevant in physics because, after all, the planets rotate around the sun on elliptic paths, and basically whenever you are tracking a particle in a potential field, being it a gravitational potential field or an electric potential field, depending on the particle's energy, the path will be an ellipse, a parabola, or a hyperbola. So those things certainly are very real in physics, even though we're going to see here that the motivation is mainly geometric. For quadric surfaces, the story apparently is not that easy because a colleague of mine who is a passing acquaintance, but who nonetheless I think is right in that, often used to say that there are no paraboloids in physics. And I'm not far enough into physics to completely verify that, but certainly I can say that, yeah, paraboloids, ellipsoids, and hyperboloids don't occur that often in physics, at least to my knowledge. That doesn't mean they aren't pretty, so there certainly are very nice examples, and they're also very helpful because we can't always just work with cylinders and spheres. We'd like to visualize a couple of other objects also. In terms of what you need to know, you definitely want to know how to what the equations of conic sections are. We're also going to talk about the parametrizations, where we're going to build some vocabulary and practice a little bit how to verify that a parametrization really corresponds to a Cartesian equation. When it comes to quadric surfaces, we're going to do the same thing. In terms of how much you really need to memorize on quadric surfaces, please double check with your teacher there. I still have to make up my mind on that also. But certainly then the last thing that is always a classic is something that you already know how to do, because the heart of classifying these surfaces, if they are given to you as a general equation, is completing the square. So we're going to see that old chestnut again too. Okay, let's take a look at conic sections. Conic sections are obtained by intersecting a cone with a plane. And that basically happens that you've got a cone here and you've got a plane that tilts. And so when that happens, if you start out with a plane that is almost horizontal, well, when it's completely horizontal, then the intersection is a circle. When the plane starts tilting, well, then the circle is being stretched, as we can see here. It's still a plane intersecting a cone, but the y dimension of the intersection is now smaller than the x dimension, so you get a stretched circle, and that's an ellipse. Then it keeps going, and when the slope of the plane is about 1, not sure, well, okay, when the slope is exactly 1, let's see if I can pull that back here. When that slope is exactly 1, then the plane, because this cone actually is also one with quote-unquote slope 1, we're going to see the equation on the next panel. When the slope of the plane is exactly 1, the intersection actually is an ellipse. That is visually hard to see because as we rotate past that, this hyperbola is visually not too different from this ellipse, which is just very stretched out, and the parabola is right the limiting case in between, the case where things change. However, then as a plane continues to tilt, ultimately, once we actually also pick up the second branch of the hyperbola in our field of vision here, we can certainly see that the intersections also include hyperbolas. Now this is, and I don't mean to toot my own horn here or just say it in a way that ultimately will show you that I also owe quite a few things to teachers. This is one of my favorite animations because this is the kind of thing, as soon as I was exposed to conic sections, I made my mind basically show this to me to show how as the plane tilts, we go from a circle to an ellipse through a parabola into hyperbolas. And as I was prepping for this presentation, I was thinking, well, yeah, I seem to be a pretty smart cookie to actually bring this up into my mind, and then I remembered, yeah, way back in high school, our high school teacher actually showed us wooden models of these things that had basically one wooden model where we had a plane that intersected the cone, and then at least another wooden model where we had another plane that intersected the cone. The first intersection was as I stopped in an ellipse. The second intersection was in a hyperbola. So that is one of those things that certainly also shows that your mind hangs on to things whether you think you'll ever need them again or not, and sometimes they're so far in deep storage that you don't even remember that you have learned them. And this is another way to potentially answer the question, why do we need all these things for, what do we need all these things for that we learn? Well, we might not know what to need them for right away, and when we need them, we might not even remember that we have learned them, but it's in there somewhere and it's not bad. Okay, end of that one. Let me get off the soapbox and let's actually talk about the computation of these things. So, conic sections are intersections of cones and planes. And so I want to now take the intersection of the plane z equals mx plus 1. Remember, this is now in three-dimensional space, so because there is not a y, this is the line z equals mx plus 1 only duplicated in the y direction indefinitely, which means it's that plane that we've seen on the previous panel. And we assume m greater than 0, just like we have seen on the previous panel that the plane just tilted up. And we want to intersect that with the cone z squared equals x squared plus y squared, which is indeed the cone from the previous panel. Well, what do? We take x squared plus y squared, right? These are Cartesian coordinates, so we don't have to worry about parametrizations and changing variables around. We just said z squared equals z squared. So x squared plus y squared is z squared, which is the same as mx plus 1 quantity squared. Then, of course, we multiply out the right side, so we get m squared x squared plus 2mx plus 1. And now we can bring everything except for the 1 over, and of course, this stuff all couples with the x, and I think I've already factored the x squared out. Yeah, okay, so we've got 1x squared minus mx squared is 1 minus m squared x squared. And we've got the minus 2mx brought over. We keep the plus y squared, and then we still have the 1 on the right side from the previous line. Okay, so now in order to see what that looks like, I want to complete the square, so I will factor out a 1 minus m squared out of the terms with x. Well, that gives me just an x squared. The minus 2mx will turn into negative 2m over 1 minus m squared. We'll leave the y squared alone. And here's what we get. We've got the 1 minus m squared, x squared, minus the 2m over 1 minus m squared x, and then we know that the term that completes the square is half the term in front of the x squared. So the term that completes the square is m squared over 1 minus m squared squared. And of course, I can't just add that. I have to add it on both sides, and I chose to really do that on both sides here, so that way I was able to put it all on one panel. And so if I take the 1 minus m squared and multiply it with the m squared over 1 minus m squared squared, I get m squared over 1 minus m squared, and that's what I've added on the right side to make sure the equation is the same. And of course the 1 and the y squared are still kept from the previous line. And then, well, then I can write this as a square, so this would be x minus m over 1 minus m squared, I think. Yeah, 1 minus m squared, x minus m over 1 minus m squared, quantity squared, plus y squared equals this right-hand side. And so if you have seen conic sections before, which is highly likely if you've seen ellipses and things like that before, then you can certainly see that this is close to the equation of an ellipse or something like that. We've shifted the center around a little bit, but we've got number times x squared plus y squared equals some number on the right-hand side. And what we're going to do now is we're going to investigate how this changes as m changes. And we're going to do that without the shifting of the origin. So we're going to simply drop this term here, so we're no longer going to investigate the same intersection, but we know qualitatively the shape is going to stay the same way, because after all, as we look at the shape, the center doesn't really matter, so we're going to keep it centered at the origin. The other thing that you can rightly say here is that the actual intersection sits in three-dimensional space, and I am not worrying about the z-coordinate here, and that is because whatever shape we have in the xy plane is just being projected up onto the tilted plane and will be the same shape in that plane also. And that's all that I'm going to say about that part. Alright, so we're actually going to look at the equation 1 minus m squared x squared plus y squared equals 1 plus m squared over 1 minus y squared. And so that is the same thing as what we had on the previous panel, only that we relocated the center. And now there are three cases, namely m could be smaller than 1, m could be equal to 1, or m could be greater than 1. What happens when m is smaller than 1? Well, when m is smaller than 1, we get positive number times x squared plus positive number times y squared equals positive number. Okay, so we can write that down as x squared divided by positive number plus y squared divided by positive number equals 1. We just divide by the right-hand side and then put everything else out here into the denominator. And that is the Cartesian equation of an ellipse. X squared over a squared plus y squared over b squared equals 1. The parametric equations of an ellipse, and that's something that we've also seen before, basically is we've got a radius in the x direction, we've got a radius in the y direction. That's actually the length of the major axis if we want to use the correct terminology. And we can see this parametrization, of course, works because if we plug a cosine t in for x and b sine t in for y, work out the squares, we end up with cosine squared t plus sine squared t, and that is equal to 1, where 0 is less than or equal than t is less than or equal than 2 pi, so we go all the way around. The parametric equations are very similar to the equations for a circle, of course, except that for a circle we've got one radius, and the difference is that for an ellipse we've got one quote-unquote radius in the x direction and another radius in the y direction. And of course that's also why an ellipse looks the way it does. It is a circle that has been hit on the head or squeezed in the sides, and in that fashion it's either flattened out or standing tall, if you will. Okay, the other thing, or another thing that can happen to this equation is that m could be greater than 1. Here's where things get a little bit more complicated, because basically what we then have is negative number times x squared plus y squared equals, and here's where it gets a little harder. M squared is greater than 1. 1 minus m squared is less than m squared, so we are ending up with something that is greater than 1 as a fraction here in absolute value. And because m is greater than 1, it's negative, so we get 1 minus something that's greater than 1, so we get negative number times x squared plus y squared equals negative number. If we divide by the right-hand side, we get 1 on the right side, and then we've got positive number times x squared plus negative number times y squared. And if we squeeze the numbers in the denominator and explicitly indicate the signs, which we typically want to do in this situation, we end up with the Cartesian equation of a hyperbola, which is x squared over a squared minus y squared over b squared equals 1. If we remember the picture, that was when the plane had tilted past slope 1, and that was something that ultimately had two branches. There are two ways to write down the parametric equations, at least. We could have x of t being a over cosine t and y of t being b times tangent t, because then again, as we plug that in, the a's and b's cancel. We end up with 1 over cosine t minus sine squared t over cosine squared t, which ends up being 1 by Pythagoras' law. And because the hyperbola has two branches, we have to use two branches of the tangent line, namely t between negative pi halves and pi halves, and t between pi halves and 3 pi halves. On the other hand, we could also use x of t being plus minus a times hyperbolic cosine of t, and y being b times hyperbolic sine of t. And again, it would end up being hyperbolic sine squared of t minus hyperbolic cosine squared of t minus hyperbolic sine squared of t, and that ends up being 1. So even though I don't know the history, this may well be one of the reasons why the hyperbolic sine and cosine are called hyperbolic sine and hyperbolic cosine. Here in this one, because these are functions on the real line, of course, we would let t go from negative infinity to infinity, and the equation of a hyperbola is this, and we can see certainly if y is the hyperbolic sine, that means that y goes from minus infinity to infinity, and the hyperbolic cosine just gives us something that looks sort of like a really distorted parabola in these two branches here. Okay, well, what else can we do? We could have that m is equal to 1, and that is at this stage not possible because we can't divide by 0. But we can certainly go back to the derivation, and in the derivation, if m is equal to 1, we would have x squared plus y squared equals x plus 1 quantity squared. x squared plus y squared equals x squared plus 2x plus 1. Yeah, we multiplied out the parentheses. Y squared, therefore, is then 1 plus 2x, and that's a parabola. It's a parabola that is opening to the right, but nonetheless, it is still a parabola. And so again, by moving the center to the origin, we see that the Cartesian equation of a parabola is x equals a y squared. Of course, we also know these as y equals a times x squared. And the parametric equations then would be that x of t equals a t squared, y of t equals t, the old trick. If you have one Cartesian variable as a function of the other, you make the one of which things are a function your parameter, and then you plug it into the other one in the correct way. And t here then goes from negative infinity to infinity, and we get the well-known picture of a parabola that is opening to the right. Okay, that should be it for conic sections, and remember these conic sections are definitely highly relevant in physics because they describe particle paths in gravitational as well as electric potentials. We're coming now to quadric surfaces, which are very nice for three-dimensional visualizations. In fact, they're also quite pretty, and again, check with your teacher to determine how much of the vocabulary you're really supposed to have down cold. I certainly want people to know what an ellipsoid is and what some of the paraboloids are. When it comes to the hyperboloids, 1 sheet, 2 sheet, as we're going to see, I'm not really sure how much of that I remember, but I would also let you know before a test how much you would have to have memorized. So, the Cartesian equation of an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And we can see why that thing is called an ellipsoid. It's sort of like an ellipse, but not quite, which means it's not an ellipse, it's an ellipsoid, right? Anytime you've got something that is similar to something else, it's something oid. Think science fiction, where you've got humans and then you've got humanoid species on other planets and things like that. The similarity to ellipses, of course, is very easily seen, because as soon as we suppress one variable, we get the equation of an ellipse, and that basically also means that all the cross-section, horizontal as well as vertical, all the cross-sections are ellipses. The parametric equations are x of u v being a cosine u sine v, y of u v being b sine u sine v, z of u v being c cosine v. Same trick as for an ellipse. The a, b, and c, as we plug things in, will cancel with the a squared, b squared, c squared after squaring, of course. And then the cosines and sines, well, cosine squared u from the x and the sine squared u from the y, both are multiplied with the sine squared v, so we can factor that out, and that ends up being 1, and then we have sine squared v plus cosine squared v equals 1, which is the one on the right side. That is basically high-end mathematical shadowboxing, as we've already seen a couple of times. That's something that you may actually want to write out for yourself. The parameters go 0 to 2 pi in u and 0 to pi in v, and so this is basically that, okay, the horizontal and vertical cross sections are ellipses, and the equations are very similar to the equations for a sphere, except that for a sphere we have one radius, whereas for these ellipsoids we've got radii, or major axes, in the 3 different directions. An ellipsoid, therefore, is a deformed sphere. It can be squeezed, it can be stretched, and that gives you then this typical ellipsoid or pill-type shape. Actually, first time I saw something like that, I thought, yeah, my dad was taking vitamin supplements that looked like that. Okay, the Cartesian equation of an elliptic paraboloid is z over c equals x squared over a squared plus y squared over b squared. Again, you can see that there are parabolas in there, because as soon as we suppress x or y, we end up with z being something depending on x squared or depending only on y squared, and so that means that the vertical cross sections are parabolas. And if we hold the z constant, well, then we get an equation of an ellipse, so the horizontal cross sections are ellipses. If we're looking for parametric equations, one way to do that would be to take the horizontal cross sections, which are ellipses, and parametrize the ellipses, and then realize that the vertical cross, the z is just c times v squared, and if we plug that in, we get exactly that, because again, a and b after squaring go away, cosine squared plus sine squared go away through Pythagoras, and what remains on the right side is a v squared, and that means on the left side we need a c times v squared. in order to parameterize the whole elliptic cross-section, we need to let u go from 0 to 2 pi. And because we want to capture all the z-coordinates that are possible, which is everything that is non-negative, we let v go from 0 to infinity. Cross-sections, vertical cross-sections are parabolas, as mentioned. Horizontal cross-sections are ellipses. And here's what these things look like. Basically, we've seen round paraboloids a couple of times already. An elliptic paraboloid is basically the same story, only that it's also squeezed on the side so that we get elliptic rather than circular cross-sections. Okay, then the Cartesian equation of a hyperbolic paraboloid is z over c being x squared over a squared minus y squared over b squared. Again, when we suppress one of the x or y variables, we get z being depending on plus x squared or depending on minus x squared, so the vertical cross-sections are ellipses that open upwards or downwards. And if we hold z constant, the horizontal cross-sections are x squared over a squared minus y squared over b squared equals number, and that's certainly a hyperbola. Similarly to how we handled the elliptic paraboloids in terms of parametric equations, we could parameterize the horizontal cross-sections with a standard parametrization for a hyperbola, such as plus minus av hyperbolic cosine u for x and bv hyperbolic sine for u. And then if you plug that in on the right side, again, the a squareds go away, the b squareds go away, the hyperbolic cosine squared u plus the hyperbolic sine squared u minus the hyperbolic sine squared u can be factored out. What we keep on the right side is a v squared, and that means that z has to be cv squared. And here, because of the parametrization, the way it's set up is u and v both have to go from minus infinity to plus infinity, because we need to capture all branches. And and then the vertical cross sections are parabolas and the horizontal cross sections are hyperbolas. I'm currently not sure if we actually need the plus minus if we let v go from minus infinity to plus infinity, but it can't hurt. Okay, so what do we get? Well, we get something that has parabolic cross sections with parabolas that open upwards in the x direction. We get parabolic cross sections with parabolas that open downwards in the y direction, and horizontally we get hyperbolic cross sections. Okay, and I think the plus minus is needed because basically for anything up here we need a plus and a minus for this one, and down here we need a plus or minus for this one, I think. So that should still work out correctly. As you can see here, I'm not too worried about all the details. The main thing for this presentation is we want to be familiar with the vocabulary, and the other thing that we're practicing here is certainly how to verify that a parametric equation satisfies a Cartesian equation, which is a good skill to practice. Okay, what else do we have? We have the Cartesian equation of an elliptic cone. That is what sometimes people also call, no, that is not a degenerate quadric surface. That is just a very special case, and that is z squared over c squared equals x squared over a squared plus y squared over b squared. Well, we know z squared equals x squared plus y squared. That is a cone, so it shouldn't be too surprising that something like that is just a distorted cone, because basically once we were to move the c squared over to the right side, we see this would be z squared, something that is conic, where the horizontal cross sections are ellipses, and the vertical cross sections actually don't have a name, because if we hold the x or the y constant, then the vertical cross section would be z equals plus minus square root of x squared or y squared plus a positive number, and for those things we don't have a name. At least, well, okay, there may be a name, I don't know it. The parametric equations, again, we would simply encode the elliptic horizontal cross sections, AV cosine u and BV sine u. If we plug that in, the a squareds and b squareds cancel. The cosine squared plus sine squared gives us 1 by Pythagoras. We end up with v squared on the right side, and that means z of uv would be cv. And then we would have u going from 0 to 2 pi, because we have to go all the way around the ellipse. And we let v go from negative infinity to infinity. That way we capture the upper and the lower half of the cone. Like I said, the horizontal cross sections are ellipses. That's why this thing is called an elliptic cone, not just a circular cone as they're sometimes referred to. And the picture, the upper half is this, and the lower half, of course, looks the same way, only in the downward direction. Okay, then the Cartesian equation of a hyperboloid of one sheet. And here, the main thing that I always have trouble with is one sheet versus two sheets. And I think the way to memorize that easily is the hyperboloid of one sheet has one negative sign, and we're going to see the hyperboloid of two sheets will have two negative signs. Either way, what do we have here? Well, if I hold x constant, my cross sections are hyperbolas because I get a y squared minus z squared equals number with some decorating factors there. If I hold my y squared constant, I get x squared over a squared minus z squared over c squared equals number. So that again is a hyperbola. So we get that the let's see, x or y held constant means the vertical cross sections are hyperbolas, and if I hold z constant, well then the horizontal cross sections are ellipses. If I want to parameterize that, again, I just parameterize the elliptic horizontal cross sections, and as I plug that in, I end up with z being plus minus c times square root v squared minus 1, and that means, again, u has to go from 0 to 2 pi because we have to parameterize the whole ellipse, and because v has to be greater or equal than 1, we have 1 less than or equal v less than infinity. And the vertical cross sections are hyperbolas, and the horizontal cross sections are ellipses. Okay, I've sort of shorted you here on not working out that this really is the z. Well, let's talk our way through that. Again, a and b cancel after we square it, cosine and sine cancel after we square it, so we end up with v squared minus c squared times z minus z squared over c squared. I bring the z squared over c squared over, bring the 1 over here, take square roots. That gives me square root of v squared minus 1 on the right side, and z over c on the left side, z of c over c on the right, and then I just bring the c over, and the plus minus comes from taking square roots. So again, something that you can work out without too much trouble using paper and pencil. And here is what a hyperboloid of one sheet looks like. Now this thing has elliptic cross sections, and actually it turns out that the shape of a hyperboloid of one sheet actually is something that is being used because the cooling towers for power plants are often shaped like hyperboloids of one sheet. I'm not quite sure what the static considerations there are that makes them shaped like that, and of course cooling towers don't have elliptic cross sections horizontally, they have circular cross sections. But either way, that is one thing where a hyperboloid of one sheet can also occur. Then we have hyperboloids of two sheets, and a hyperboloid of two sheets, well, I think really I just realized that, okay, the one with two sheets has two negative signs. And again, we've got the same story. Let's see, if I take a vertical cross section and hold the x constant, I get z squared over c squared minus y squared over b squared equals number. So that is a hyperbola. When I hold the y constant, I get z squared over c squared minus x squared over a squared equals number. So that's a hyperbola. And when I hold the z constant, well, then I have to make sure I add enough, because I have to compensate, or I add enough so that I get a negative sign on the right-hand side. So then after all the negative signs cancel, I end up with x squared over a squared plus y squared over b squared equals number. And that would be an ellipse. Again, in terms of a parametric equation, I would parameterize the ellipse. After I'm plugging all this stuff in, I'm keeping a negative v squared, right? And the negative v squared can be brought over to the right side. And then after taking square roots and multiplying by c, I end up with this equation for z of u and v. U has to go from 0 to 2 pi again, because we have to go around for the whole ellipse. And v goes from negative infinity to infinity, because this time around we don't have to worry about the square roots here. The vertical cross sections, as indicated, are hyperbolas. The horizontal cross sections are ellipses. And the way this looks is right here. It is something that is actually decoupled. You may want to say, how can that be with with v going from minus infinity to infinity? Well, remember that z between negative 1 and 1 is out, and actually here I could have let the v run only from 0 to infinity, because in this fashion I think we're actually running through the whole surface twice, because the negative v's just parameterize the ellipse slightly differently, and we're getting the same height. Okay, so I could have gotten away with a 0 here, but that's that's quite all right here. We're not going to compute the area of an infinite object because that would of course be an infinite number. Okay, so that's a hyperboloid of 2 sheets. And then really the one thing that we can do computationally is that we can classify quadric surfaces, and here is where basically we're getting back to completing the square on steroids, and the classification itself, then that task is what requires us to be on top of the vocabulary. So for example, if I gave you this equation, 3x squared minus y squared plus 4z squared plus 6x plus 8y equals 1, and I want to know what that looks like. Well, I can't say that from here, even though I've got an x squared with a plus, a z squared with a plus, and a y squared with a minus. So that ought to be a hyperboloid, but is it 1 sheet or 2 sheets? And even though there's one negative sign, you can't quite key in on that, because as we're going to see, well, in order to really determine what's going on, I would have to complete the square. Okay, so let's see. So I would first sort, and that means I keep the 3x squared and pair it with the plus 6x, and that's what we have here. I keep the minus y squared and pair that with the plus 8y, and that's what we have here. And the 4z squared, of course, just has to be copied, and we keep the 1 from the right side, of course, also just here. The term that completes the square for this one will be 1, and that's because I first have to factor out a 3, and I have x squared plus 2x. So I get 3x squared plus 2x plus 1 minus 1. And here I've got this extra negative sign, so I would have minus y squared minus 8y. So that would actually be the term that completes the square, would be plus minus 16, and we have to be careful with negative signs. So let's see how that works out. We factor out the 3x squared plus 2x plus 1 minus 1. I don't want to mess with the right-hand side here. Then I have minus y squared minus 8y, as we've seen here, and then half this one squared gives me the term that completes the square, so plus 16 minus 16. Of course, the 4z squared just stays as is. And now I can bring things over, because now this is 3x plus 1 quantity squared. Okay, right side is 1 still. The left side is 3x plus 1 quantity squared, and then 3 times negative 1 is minus 3. Then we have minus y minus 4 quantity squared plus 16, because minus 16 is plus 16, and we've got the plus 4z squared. And now we realize that the minus 3 and the plus 16 gives us plus 13 on the right side, which would, as we bring it over and combine it with the 1, give us a negative 12 on the right side, and that's indeed what happens. So we have 3x plus 1 quantity squared minus y plus 4 quantity squared plus 4z squared equals negative 12, and we divide by negative 12, and that gives us minus 1/4 x plus 1 quantity squared plus 1/12 y plus 4 quantity squared minus 1/3 z squared equals 1. And that actually, because we have 2 negative signs, is actually a hyperboloid of 2 sheets. Now, the other thing that you notice here is that this is not the same equation, because the equation that we had in the standard example was that we had negative signs attached with the x and with the y. The shifting of the origin, of course, is not that bad, and you can see, okay, here this one and this one should have been a minus sign. That's a simple copy error. Let me fix that real quick. And now it's fixed. I think you probably have already seen that as we were following along. Man, we had such a nice presentation here, right? Almost no mistakes, and then there's something silly at the end happening. Hey, I might as well leave that in. You can just see here that sometimes these things can and do happen, even though, of course, I would have to give myself at most a 9 on an exam problem here, if that was an exam problem. What you can see here is that the minus signs are attached to z and to x, not as in the standard example where they were attached to the x and the y. The only thing that means is that the axes are interchanged. Most likely this hyperboloid of 2 sheets, rather than sitting like this, sits somehow like this with the sheets sticking out towards the sides rather than towards the bottom and the top. And again, shadow boxing here, this is the kind of thing that you want to be able to visualize. And so basically that means all these standard equations can also, when they have negative signs, occur in other ways, with the negative signs being attached to other variables. And all that means is that the figure is being rotated around, and that is not that bad in terms of recognizing it. You just have to make sure that when you draw it right. If you work it out with a computer algebra system, your computer algebra system will certainly, after you put the correct parametrization in, do that correctly for you also. Okay, so we've seen some really neat two-dimensional as well as three-dimensional stuff. We've visualized. I think we should be very familiar now, definitely, with the equation of an ellipse as well as with the Cartesian equation of ellipses and hyperbolas and parabolas. And that really was the main goal of this presentation, aside from building up the vocabulary as necessary. With that, homework shouldn't be too bad on this one because it's really just completing the square and a little bit of vocabulary. Have fun with it, and I'll see you in the next one.